Hello, this is part 3 of chapter 1 where we are going to discuss further about measurement and what to do with that data that you collected. So before we jump into that, let's discuss about what type of numbers that we use in chemistry. We mainly use two different types of numbers, or we come across two different types of numbers everyday life. One is exact number, one is inexact number. What is an exact number is any number that you can count them out just by looking at them. For example, if you look at my hand here, you will see 5 fingers. How do you know? Because you are currently looking at it and you are able to separate one from another. So these are called exact numbers because there is no ambiguity in it. And also another type of exact number category is if it is part of a definition. We already know that a kilogram means 1,000 grams from the relationship of the definition. So it is exact. Like, how 1 dozen has 12 eggs, we already know that most commonly. So if it is something that you can achieve by counting, by looking at it, or coming from a definition, you call them as exact numbers. Exact numbers wouldn't pose any issue to us whenever you're doing calculations in chemistry or in science. However, inexact numbers will pose a challenge because it is always challenged to measure accurately. You could only measure it with the certainty to the last digit that we are going to discuss in next couple of slides what it means. So an uncertain number or inexact number means it comes from by measuring something, like by taking a length of it, by taking a mass of something, or by taking a volume of it, or by counting time or speed of it. All of these, when you try to measure, there is always some amount of uncertainty present. What it means is you could estimate to your best guess what the measurement that you are measuring, but you cannot be so sure that it is exactly accurate that you measure, just like an exact number. Like you can be sure that there are 5 fingers, but if you try to measure the length of my hand or width of my each finger, you can estimate the last digit, but you cannot be sure. So counting 5 is exact number, but trying to identify the measurements of length or width or mass of these fingers is a challenge because these comes from measurement. So we call these as inexact numbers. So that's where comes the significant figures. So significant figures will help us to refine the number by defining which numbers we should consider, which numbers we should discard when you measure something or when you calculate something. Okay, this topic is very important, not only just in this chapter, but in the entire scientific world. Whenever you try to use any measured numbers in a calculations, your answer should always be respectful to the correct number of significant figures of your data. So we are going to discuss what it means in this chapter a lot. So just by definition, significant figures are the meaningful digits in a reported number. Which means, well, I'll show you some examples. So an example of a significant number is here. It said when you try to measure this memory card, you could estimate that it is about 2.5 centimeters. But you could, you couldn't doubt that it is at least 2 centimeters to a certainty, but you can always doubt that is it really 0.5 or zero point 0.4 or zero point 0.6, because you're trying to estimate that last digit. So significant figures always have a certain amount of certainty and a last digit, which is always an estimated number. Okay. So you could pick, just because it is an estimated number, there is always a prone to error that we can call that it could be a 2.5, or we can say it is only 2.4 or 2.45. So that's why we need to use the theory of significant figures to consider which numbers are important when you measure something, which numbers are not important. So we have set of rules, mainly 4 different rules that we follow to identify which numbers are significant, which numbers are not, to report. Let's say one rule is that any non-zero digit is significant. So let's say you measure something and you come up with a number that has all non-zero digits. So you can tell all those numbers are significant without any uncertainty. And the rule number 2 says that zeros between two non-zero digits will make the whole number or whole numbers in that particular digit is significant. So it just as the rule number 1. So it doesn't matter if you have zeros here in the middle, still that will make the whole number as significant figures. So this number 305 has 3 significant figures. And this number 50.08 has 4 significant figures because these zeros are present between 2 non-zero digits. Okay. From here, it's going to get a little bit complicated. Rule number 3 will always complicate things for most students. Any zeros, any number that starts with zeros, it does not have to be included as significant. So the zeros on the left side of a number are never significant because zeros are saying what is the decimal place of the measurement, but they are not actually saying that it is part of the measurement. So part of the measurement here for this number 0.0023 starts only at 100th decimal place, like third decimal place. So just saying what is the magnitude of the number, but it is not adding to the any accuracy by having 2 zeros. So those zeros are not significant if they were on the left side. Again, even in this number, these zeros are not significant. So you only have 1 significant figure here. Let's look into other numbers here. The number of significant figures. Another rule is that the 4th rule. This conflict with the 3, or it is kind of opposite to 3. Let's say you have the zeros on the right side. They were significant if they were preceded by a decimal. Because if the decimal is present before the zeros, we are saying that we're pretty sure until the third decimal place here that this number we calculate until 1.200. Remember, the last digit is always uncertain digit. So you're saying this number is significant, this number is significant, and you only uncertain about last 0. So by having the zeros even after decimal, we are saying we are confident to the third decimal place in this number. So zeros after decimal are always significant. And the 5th one, so there is no hard and fast rule. Here, you could either consider this one as significant or not significant if you have zeros after a number with no decimal. So sometimes you can call all the numbers as significant, sometimes you don't have to call any zeros as significant. So one thing you could do to avoid the ambiguity is you can use this scientific notation. We can talk how to work on scientific notation, maybe in a different video, or let me pause this video and get my another PowerPoint slide to add the topic here. So I'm going to show you how to use the scientific notation, so you will have that information as well. Oh, it's still recording. Okay. So scientific notation is a way to shorten the large number into a small number. And for that, we use this type of expression. We say in the form of y to the power y times 10 to the power of x, where y has to be a number between 1 and 9 and x has to be a number, or x can be a positive or negative number. So based on if x is positive or negative, you could predict is the magnitude of y. Let's say if x is positive 10, now you can think of something near billion for the y. If x is negative 3, now you can think something like in micro, or yeah, micro for in terms of magnitude of y, so smaller. So let's see how to write this scientific notation. So if you have a larger number, how do you convert to scientific notation is, you need to, if you have larger or smaller number, you need to find a number between 1 and 10. So for 2500, the possible number that you can find for 1 and 10 is somewhere near between 2 and 5. And for this number 0.036, the number that you can find between 1 and 10 is somewhere between 3 and 6, right? So let's move the arrows towards those numbers. So depending on if you're moving left or right, your exponent value is going to be decided if it is going to be a positive or negative. So if you move to the left, which means you are making larger number into a smaller, so your x has to be a positive number for the decimal places that you move to the left. And if you move to the right, you are increasing the value of the number to reach to the number between 1 and 10. So you need to have the negative exponent so that you will have the correct magnitude for that number. So because here for 2500 you move 3 decimal places, and here you move 2 decimal places, you should have exponents of +3 and -2. So for the 2500, you will have the scientific notation as 2.5 times 10 to the power of -3, whereas for 0.036, you should have the number of 3.6 times 10 to the power of -2. Okay. So let's say, how do you convert the scientific notation number already presented into a normal number? It's kind of opposite to what we just did. Let's say if you already have number in scientific notation, how do you convert it back is depending on if you have a positive exponent or a negative exponent. If you have a positive exponent, which means the number is actually larger but made it look smaller. So to make that number larger, you need to move the decimal places to the right side. So you need to move 2 decimal places because you have exponent 2. Awesome. So if you have a exponent negative, you achieve this negative to have a number between 2 and 8 because that number is smaller. So to make that number smaller, again, you need to move the decimal places to the left side of that number. So it should look like 0.0280. So that's all you need to know about scientific notations. It is not in part of your useful lecture slide. That's why you opened up another lecture slide. So let's go back to our actual lecture slide. Think it is there. All right, we are back here. Now let's see, where are we? So we just discussed what our scientific notation is. So whenever you have a larger numbers like this, to avoid the ambiguity, you could just convert that number into scientific notation so that you would know how many significant figures are there. All right. Let's practice what we just learned. We learned about 5 different rules on how to predict the correct number of significant figures in a given number. So whenever you see a problem with lots of empty space, my expectation is that you would pause the video, work on those problems, and check the answers so that you can just correct your mistakes right away here. So it just saves lots of time for you in future, because you're already checking yourself if you understand the topic or not right away. So let's look into these problems. It gave different numbers and it is asking you to identify how many significant figures are present. So Until you get really comfortable with them, I need you to refer to the significant figure rules that we discussed previously. Then only identify, okay, then only label which rule you are using, then give the answer. It just, avoids the possible mistake that you might make. Even smart students make mistakes in this because they don't pay attention to the rule. So let's see your answers. So for A, you should follow rule 1, which says all non-zero digits are significant, so you should have 3 significant figures. For problem B, you should use rule number 2, where it says a 0 between 2 non-zero digits is always significant, so you should have 4 significant figures here. And for C, you should use rule number 3, which says that if you have zeros in front of a number, those zeros are not significant because they are not contributing to the measurement. So you should have only 3 significant figures here. And rule number 4 says that if you have zeros after decimal, they were significant because they were adding to the accuracy even after decimal place. So you should be having 4 significant figures in this number. And let's say if you have 50, you can say the 1 or 2, both are right answers. But I suggest you use scientific notation, converting to 5 times 10 to the power of 1. So for sure, accurately you can say that it only has 1 significant figure. So there will be no debate. And for this number here, very challenging problem it looks like, right? So if you have zeros in front of a number, they were not significant, but zeros after decimal, they were significant. So 1 0 it doesn't count, but another 0 you count. So you should have 4 significant figures. Now let's check the answer. So 3, 4, 3, 4, 1 or 2, 4. That's how you should be getting. If you did not get any one of them right, just read the rule again and try to understand and apply it on different problem. Then you can quickly move on to bigger challenges than trying to identify what are the correct number of significant figures. All right, let's move on. Let's move on to the next problem. All right, now that you know how to identify how many number of significant figures are there in a given number, now it is not just enough to know how to identify significant figures in a given measurement, but you should also apply certain rules whenever you have a measured values that you include them in a calculation. So there are 2 different rules for you to follow. You must follow this, otherwise your predicted answer wouldn't care if you actually paid attention to significant figures when you measured or not. So there are 2 different categories that you need to follow. When you use these significant figures in multiplication or, well, I think we are using addition and subtraction here, okay? Control my enthusiasm for multiplication and division for a moment. So if you're using significant figures in a calculation such as addition or subtraction, the rule says that to have the similar accuracy to the measured values, your final answer should have the same number of lowest number of decimal places to one of the given number. And it sounds complicated, but when you look at the problem, it looks very easy. Let's say you're adding these 2 numbers. One number has 2 decimal places, another number has 3 decimal places. So your answer can only be now accurate up to just 2 decimal places because one of the number is only should about until 2nd decimal places. So you should round up your number to just only 2 decimal places. So how do you do that? Is by cutting out the last number. So you will have number the answer as 102.73. In just a slide or 2, I'm going to show you how to cut off these numbers. There is again a method to round up these numbers. So converting this number to this number is called rounding up numbers. So we have 2 sets of rules to follow. I'm going to show you in a slide or couple slides what is that method is. But for now, just trust me that it is the correct way of rounding up this number. Now let's look into another problem. So your subtracting 20.1 from 143.29. So one of the number is only sure up to one decimal place, but another number is sure up to two decimal places. Because you are using the less accurate number in the subtraction or addition, your answer can only be least accurate as your least accurate number. So right, so you should cut off the second decimal place here. So you should round up that number of 123.192 to 123.2. Again, how it happens from 1 to magically 2, I'm going to discuss soon how to do that. For now, just trust me. All right. So let's discuss in the case of multiplication or division. Say you need to do multiplication or division. When you do multiplication or division using a significant numbers, you should have a different rule than what we just used in the previous slide for addition and subtraction, which is that the number that contains the least amount of significant figures, irrespective of the decimal place, the number that contains the least number of significant figures will be responsible to decide how many number of significant figures should there be in your final answer. So you shouldn't have more significant figures than one of the least number of significant figures. That's the only rule. It looks less complicated for sure than the previous one. Now, let's say you were multiplying 1.4 with 8.01, 8.011. So one of the number has only two significant figures, but the second number has four significant figures. So you cannot have your answer in more than two significant figures. Otherwise, it will be just a predicted number, but not an accurate number. So you need to round up the 0.2154 into just two significant figures. So you're going to remove all of this part here, and you're just going to round up to just 11. We will discuss how I'm able to do this in a slide or two. And let's say you're doing this math of you're dividing 305.88 over 11.57. So one of the number has four significant figures, but the other number has five significant figures. So you are only allowed to have just four significant figures in your answer. So 1, 2, 3, 4. So you need to cut these two numbers out. So you're going to round that number into 0.03783. Okay, this is the number that I'm keeping, but I have to change it to 3 this time. I'll discuss how. Let's see. So those are two cases that you must remember. Are you doing addition subtraction so that you can pay how many decimal places present, or are you doing addition, are you doing multiplication or division so that you will only care about least number of significant figures? All right. And in some cases you will work with exact numbers. Exact numbers are considered as infinite numbers, and it has no effect in deciding how many number of significant figures you should have in your final answer, because exact numbers are not measured numbers. So it might come with just one number or two numbers because there is some ambiguity, right? So we don't use them towards counting to the how many significant figures you should be having. Let's say you are doing the math of counting 3 pennies of masses that each contains 2.5 grams of mass. So your answer shouldn't just take care of the exact number as a significant figure. So here you have two significant figures. So you're going to have your answer with two significant figures because that is the inexact number, or in other words, a measured number. So, however, so far, I feel like I'm going a little bit fast. Let me slow down. So far, we discussed about what are significant figures are and how to identify them. And then we discussed how to use them in calculations. So now we are going to discuss, let's say you're doing this series of calculations. Should you be doing roundup of numbers immediately or at the later? in general, you should not round up the numbers in the middle because you might end up with a wrong number or wrong answer at the end. So do not start rounding up the numbers in the middle of the calculations. I know I yet to teach you how to round up the numbers. In this slide, I'm going to teach you how to round up the given numbers or the calculated numbers. But I want you to not to do them in the middle of the calculations because they are going to mess up your calculations sometimes. So here are the rules to round up a number. So if you know how many significant figures you need to keep, you would know what is your last number is. So the number that is next to it can be a number between 0 and 4 or 5 and 9. So if it is between 0 and 4, you will just drop that number and make no changes to the number that you are keeping. Or in other case, if that number is between 5 and 9, you will drop that number, but you will add a +1 to the number that you are keeping, right? Either you just simply drop or add +1 by rounding up. So it can be the rounding down or rounding up. So again, let me just warn you to not to use these two rules when you are in the middle of the calculations. You need to wait until you finish the series of calculations. Here you can see why. Let's say you start rounding after each step to only 30.9. You don't have what is the next number is in this calculation here. And you do the next calculations with the rounded number, you end up with 65.2. Let's see, if you didn't round up after first step, it should look like 30.93. And if you do the calculations with it, you are ending up with the number of 65.3, which is incorrect in this case. So that's why you shouldn't round up the numbers in the middle of the calculation. So you should always wait until the last step. Okay. All right. So we are going to apply what we learned over significant figures, how to identify significant figures, and how to use them in the calculations in this huge problem. So my expectation of you is to pause this video, practice this on your own, and compare the answers that I'm going to work on here. Then see if you need more help or you're good to go. Okay. Let's see. The question is asking you to perform these calculations and present the answer in a correct number of significant figures. So what I'm going to do is I'm going to work on these problems here. Starting with A. So the first problem is the addition. So whenever you're doing addition, the rule says that you should pay attention to the least decimal places. Then your answer should be in those many decimal places. Now if I do the calculation here, it will be 317.5 ml plus 0.675 ml. In here, this is where I'm going to pay attention because it only has one decimal place, whereas here I have 3 decimal places. I don't need this information. So I need to make sure my answer only has 1 decimal place. So if I count these two, I should have the answer as 318.175. Because I'm keeping the number to only 1 decimal place, I'm going to drop this number, but 7 is the number between 5 and 9, so I should add +1 to the number that I'm keeping last. So I'm going to convert that 1 to 2. That will be the correct significant numbers, and the unit is ml that we shouldn't forget. Second problem, excuse me. B. So problem B says that please subtract. So again, we are going to use the same rule that we just used. 47.80 liters minus 2.075 liters. So one of the number has 2 decimal places and this number has 3 decimal places. So my answer should only have 2 decimal places because I'm performing subtraction. So if I do the math, I should have the number of 45.725 liters. But I'm only allowed to have just 2 decimal places. So I have to drop this third number here. So 5 is a number between 5 and 9. So I am going to round up 2 to 3. So my final answer will be 45.73 liters. That will be the correct significant figure. Let's work on C. So C is doing a division. So division rule says that your final answer will have the same number of significant figures as one of the least significant figure digit. So let's see which are how many significant figures that you should have. 13.5 grams over 45.18 liters. So top number has 3 significant figures, bottom number has 4 significant figures. Because 3 is smaller than 4, my final answer I'm going to aim for to have only 3 significant figures. So if I do the math, the number will shown up to be 0.29880478 grams over liters. That is a too large number, but I'm only allowed to have just 3 significant numbers. So I'm going to drop the fourth number 8. So 8 is a number between 5 and 9. So I'm going to round up the number 8 to 9. So grams over liters. That. Let's try to do D. D is doing a multiplication. So I'm going to use the same techniques that I use for problem C here. Have the least number of significant figures. So 6.25 cm multiplied with 1.175 cm. This one has 3 significant figures. This one has 4 significant figures. So my final answer can only have 3 significant figures. So if I do the math, the number shown up to be 7.34375 centimeters square. So because I can only have 3 significant figures, I have to drop this fourth number 3. So 3 is a number between 0 and 4, so I don't have to do any rounding up. So it will be just 7.34 centimeters square. That will be our answer. So let's work on problem E. Okay. So problem E is doing an addition, but if you pay attention there, both the exponents are not of same magnitude. So whenever you're doing addition or multiplication, it will be more convenient and accurate to convert them into same exponent. So to convert, I'm going to add 5.46 here times 10 to the power of 2 grams, and we're trying to add 4.991 to the 10 to the power of 9, but I want to cut down one exponent from 3 to 2, so I want to move to right. So I want to say I have 4.91 times 10 to the power of 2. So I change exponent 3 to 2 here. That's why I moved the decimal place to one place here. Okay, so if I do the math, I will have the number of 55.37 times 10 to the power of -2 grams. Okay, so one of the number has, well, here I was just about to make a mistake of thinking about multiplication and division. So because in this case we are doing addition or subtraction, you should have the same number of decimal places to the lowest number of decimal places, but fortunately here both the numbers here has 2 decimal places, so this is the correct answer already because it already comes with just 2 decimal places. Now just to present the number to same as it is given, or just to show you that using scientific notation, is it going to change the number of significant figures? So you can also write 55.372 5.537 times, excuse me, 37 times 10 to the power of 3 grams. Just converting into a scientific notation does not change number of significant figures. That's why I can either write like this or write like this. But I always suggest you to write the final answer in the scientific notation. So let me just take this check away, because it is much more scientifically correct to present your answer in a scientific notation. So it is very easy to read for the reader, and it is most common way to present the answer. Okay? I hope that you successfully completed all of these 5 problems and got the right answer. And if you didn't, it is not a problem. You just practice a couple more problems and you will be fine. All right, let's work on last problem in this section, and then we just have a small topic to end this lecture. So this problem is saying an empty container with a volume of 9.850 times 10 to the power of 2 centimeter cube is weighted and found to have a mass of 124.6 grams. Okay, you were given a volume. So far I see you were given some volume. You were given a volume and you were given a mass. The container is filled with a gas and reweighed. Okay, the mass of the container of the gas now after reweighing, after filling of the gas, is 126.5 grams. So it is asking you to determine the density of the gas to appropriate number of significant figures. Even the question doesn't say appropriate number of significant figures. You should always present your number in correct number of significant figures. Now let's work on this problem. I'm going to show you how to work on this problem. So in our previous lecture, we discussed the relationship between density to mass and volume. I told you that density is related to mass and volume as a fraction of mass over volume. So do you have the enough data? What I see is you're given the volume directly in centimeter cubes. That's awesome. Do you given the mass directly? You're given 2 different masses. So how do you get the correct mass is because you're asked to identify the density of a gas, but not the container. So you're going to take the difference between masses and identify what is the mass of the actual gas. So mass of gas, you're going to identify by taking the difference between, excuse me, 126.5 grams minus 124.6 grams. We are doing addition and subtraction, so decimal places you need to pay attention to. So your answer should be 1.9 grams. It looks like your decimal places are in the right place. So you got the mass now. So let's identify the density. So mass is 1.9 grams. And the volume is 9.850 times 10 to the power of 2. So now, if you do the calculations, you will have the units here is centimeter cube. You will have the answer at 0.00193 grams over centimeter cube. Okay. Grams over centimeter cube. Now, let's get to this answer to correct number of significant figures. Because you are performing division here, you should have the same amount of significant figures to one of the lowest significant digit. So here 1.9 has 2 significant figures, and the following number here has a lot more significant figures. So you're going to have only 2 significant figures in your answer because this number has 4 significant figures. How do you cut short this one into just 2 significant figures? Is you're going to keep these 2 numbers and you're going to drop 3. So 3 is a number between 5 and 9, so you can just simply drop it. So your final answer is going to be 0.0019 grams over centimeter cube. And I said that it is much more nice to convert any number into a scientific notation. So you can just convert that 0.0019 to scientific notation by moving the decimal places to the right side 3 times. So you will find a number between 1 and 9. So it should be written as 1.9 times, times 10 to the power of -3 grams over centimeter cube. This is the perfect way of solving this problem. Whereas the ink, maybe you can read the bottom information. All right, just last 2 slides. We are close to finish this lecture. I know it's a long lecture, but for very right reasons, it is a long lecture because all the information we discussed is very important for this chapter and also for rest of the year, actually. Okay, so let's get over with discussing what is an accuracy and precision means. Whenever you're performing an experiment, your results should have the precision and accuracy as well. So an accuracy tells us how close your value to the actual estimated value or true value, and a precision tells how correct you are over the repeated experiment course. Let's say try to throw the pepper waste into a bin. If you're able to put all of them in one container, you have both good accuracy and precision. But in this case, let's say in the second case, you throw them all out, you're not able to put them into the bin, but they were all at the same place, so you can say that you don't have, well, in this case, we can say that it has poor accuracy, but good precision. Let's say in the third case, they were all over, then you will say it has neither accuracy nor precision. So let's look into this scientific case. Let's say there are 3 different students that weighed a sample of 0.370 grams of aspirin, and they come up with different numbers. So our sets of 3 experiments. Let's examine their accuracy and the precision. So student A has the data of 0.335, 331, 333. They were far from expected value of 0.370, but they were near to each other. So student A has good results. Well, student A results are precise but not accurate, we can say. Student B has results of 0.357, 0.375, and 0.338. They were scattered. Because they were scattered, you can say that they were not precise and not accurate. Student C come up with the values of 0.369, 0.373, and 0.371. They look pretty close to expected value of 0.370, so you can say they were both accurate and precise. That's all you need to know about accuracy and precision. That's all for part 3 of this lecture, and I'll see you again in part 4 of this lecture. Remember, this lecture is very important, not just for this chapter, but for entire year of general chemistry.